Yesterday, we had a very interesting discussion in the lab sessions, and it was about comparing loops to recursion. And I want to share some of those insights with you because we don't record the lab sessions. Imagine you need to find the maximum in a data set, say a list. What you can do is you can just implement find max for a loop on some sequence where the sequence could just be a list. What I can do is I can just pick the first element and say that's my maximum so far. And then I go through the elements in the sequence. And if the current element is greater than my maximum so far, the maximum will be updated. And I'm returning eventually that result. That's something fairly easy that you have done. I know it's not perfect. It fails for an empty list. We'll look at the first element again, but it's not a programming course or a software engineering course to cover the empty list, whatever. We just assume the list has at least one element. And then that's at least a start to implement this with a loop. But now, in one of the lab problems, you're tasked with implementing this using recursion. And how could you do this? We could try to implement this now. So we could say this is find max 1. And how can I do this in a recursive way? I could just cover the base case and I say, well, if there is one element in the sequence, then I'm just returning that one and I'm done. So I don't need to do the recursion. But if I have more than one element, I'm unable to decide this immediately. What I need to do here is I need to do divide and conquer because I have my sequence, my list, and I'm unable to determine it for the whole list. But what I could do is I could take the first element and leave it aside, so element 0, and then find the maximum for all the remaining values, so starting index 1 as of the second element. And once I have found a maximum for the remaining elements of the list, I can compare this to my maximum, or I could compare it to my current element, element 0. So I'm comparing the maximum of the remaining list to that one element I have left aside. And this is something I can do very easily with recursion. So what I could do is I could call recursively find max 1 on the remaining sequence, and I would get some result, which is a maximum. And again, if there is more than one element, we would again have to do another recursive call and so forth. So I would get some value, which is a maximum. And then I could check, for example, if my S0 is greater than the maximum, then I could just return S0. I could also say otherwise I'm returning M because if M is greater than S0, then M would be the maximum. I could do something like this, but it turns out I can do this much simpler in Python because in Python there is a max function which comes natively with the language. So I can actually say, what's the maximum of S0, the element, or the maximum that comes from the recursive call. So this is exactly divide and conquer. And I determine the maximum and I return it. So just in order to better understand it, again, I'm unable to decide what the maximum is for the whole sequence, so I leave the first element aside, try to find the maximum for the remaining list. If that's still not possible, then again, I leave one element aside for the remaining list until there's only one element left. That's the one that is then being returned from the last recursive call and then compared to the element before, and then the maximum of those two is being returned, and then the recursion step by step goes backwards, and eventually at some point we have a maximum for the remaining list, and we compare that maximum to S0, and we return the larger one. So this max here, that's not a recursive call. That's just a function that comes natively with Python. We can check if this actually works. Say we have our data, which is 1, 5, 2, 110. Let's say -4. And we can see if find max works. You can see find max of the loop, or find max loop of our, not S, of our data returns the 100. We can also try to implement this for find max 1, and it also returns the maximum. Now, which one is faster? Possibly the loop is much faster than the recursion. We can try to test this now. We can say time it, we can say find max loop of the data. And it's run many times. So this takes 79.9 nanoseconds, the loop one. And we can compare this now to find max 1. It's called find max 1 because soon we will see if we can actually improve the recursive implementation. And we will see that this takes 454 nanoseconds. And now as we make the data larger, probably the difference is even much bigger. Because for the recursion, what we need to do is we put more on the stack, so recursive calls always lead to some extra work in the operating system, which we have studied before. Now, the question is, say, I want to keep the recursion because there are also some programming languages that only allow you to do recursion. So maybe you should develop a better understanding of recursion. Some programming languages are very, very efficient in executing recursion and do not offer loops. So what we can try now is, can we improve the recursive implementation? What we are doing here is the slicing. And slicing actually leads to some overhead because what I'm passing is not the whole list, but actually the list starting the second element, so as of index 1. And that also leads to some work because I cannot just pass the object to S, but rather the slicing would somehow lead to a new list. And let's try to implement this now and try to improve that we don't need slicing, but we can do something different. And maybe we want this to work also on a larger data set. What we can do is now, I just want a larger data set, say just a data set of random integers. So what I can do is, I can do something like this in Python. I can import a random package, and random.choices from a range here would mean that I sample from the range of 0 up to this number here, where the upper boundary is excluded. And I can either have one sample or I can have k many samples. So say 2,500 samples. And what's in data, we can just see the first 10 entries in the data. So we see we just have random integers in here. And we can do the time it again for find max loop and see how long it takes. So this takes 15 microseconds with the loop, and the inefficient recursive implementation is being run. We'll see the result very soon. So it takes quite longer, 6.3 milliseconds. And our goal is now to improve the recursive implementation. So we don't need the slices, but we can actually try to speed it up. What you will notice is obviously you can make K much larger. And you can run this with the iterative version, the loop. But if you make K much larger, the recursive one here, at least in this Python ecosystem, it will easily lead to a stack overflow because we have reached the maximum number of recursions possible. We can try to increase this, but we'll keep it now to 2,500, just as an example. And as I said, there are other programming languages that don't have loops, but they can run recursion much faster. So you could also make this as a much bigger data set. But we'll keep it at that size now. What I want is to improve the implementation of findmax1. So we don't need the slicing, but we can actually just pass the reference of S through, and we don't need slicing. So we go back to the implementation of findmax1. We call it findmax2. And we need to add one parameter. And the parameter is an index k. So the current index I want to look at. And this will have a default value 0. So I can just call findmax with my data. And I don't need to pass a value for k because it starts looking at the first entry. And what I would want to do is I need to update somehow this case here, because before the edge case said I only have one element left, and this would happen eventually when I keep slicing and slicing and I always leave one element aside, I only have one left. But we don't want to do the slicing anymore. So I want to do something different later. And that's why our list is not getting smaller and smaller, but rather what I want to do is I want to keep passing S, and this is the recursive call on findmax2. So I keep passing my list, just a reference. I'm not changing the list or making it smaller, whatever. And I have my index k, and initially I'm looking at k is 0. And that's why I'm putting here now index k, because I'm not comparing the 0th element anymore, but element k, which is initially 0, but later k will be changed. And then when I do my divide and conquer, I say, well, initially I'm looking at index 0, and I'm comparing that element to the findmax result of the remaining list, leaving out element 0, but I'm not using the slices to keep the list smaller, but rather I just keep moving that index where the next part of the list I want to investigate would be starting. So what I'm passing is k plus 1. I'm increasing k, and then in the recursive call of findmax2, what I'm doing is I'm starting to look at index 1, which would then be k equals 1, comparing it to the findmax result of the unchanged sequence with k plus 1 again on top, which is then index 2. That means I keep just increasing that index. I'm not changing S like I have done with the slicing. So here I need to do something different. I need to stop when k has reached the maximum index. And the maximum index of would be k plus 1 would be the length of S. Because imagine I have a list of 100 entries, and then index 99 is the maximum index I'm allowed to use, because index 100 would be invalid. So if k plus 1 is the length, then k has reached the maximum value. I could also just say where k equals to length minus 1, so the length of S minus 1, but I think additions are easier to understand than subtractions. And then I'm also putting here index k, because then when k plus 1 is equal to the length of S, then k is the maximum index. So that's the last element I'm looking at, and that's the one I would be returning. And that would go back to, so that would be the last recursive call, and then element k would be put in here, and it would be compared to k minus 1. So in the recursive call before, where k had was minus 1, the current k. So we can see that this works just on our example like we had before. We said something like we have this small data set here, and we run find max 2 on this data set here, and we see it also returns the 100, which is the maximum. So it's very important you don't put a 0 here, because we keep changing k, and we're not using a slicing to make the list smaller. And now actually, let's see if this runs faster than the find max 1. So we have this large data set. So data is still our large data set, or large, relatively large with 2,500 elements. And now I'm running the timeit, and you see it runs much faster actually than the find max 1, because in find max 1 we needed 6.3 milliseconds, and actually it took quite long because we used this slicing in here. So we've sliced the list and we couldn't just pass through a reference to the list. So it's about 30 times faster because it's only 218 microseconds, while doing the slicing is 6.3 milliseconds. Obviously, the iterative one is still much faster. It's 15.1 microseconds. The recursive one here is slower, but Python is also not made to run or to execute recursion super efficiently. There are other programming languages for that. And this exercise here, the coursework and the discussion I'm providing now is meant for you to better understand divide and conquer. So we are unable to find a maximum for the whole list. So rather we take the current element aside and compare it to the maximum of the rest of the list. That's the idea of divide and conquer. In Python, it's super short because we have the max function. If you don't have the max function in your programming language, you just compare this value here in S0 and the maximum returned here. So it's just an if-else, as I have done before, but we're in Python, so we should also use the max function wherever possible. And we see not doing the slicing, but just using an extra index that we keep moving massively speeds up this recursive implementation. I hope this helped you to get a better understanding, and happy learning.